Hello, good evening. Today is November 18th, and I'm recording this video presentation to be given at the SDPS, Society for Design and Process Science, a workshop on smart systems, and that's going to be on November 20th. And this is a placeholder presentation. So I've got 20 minutes and I've got about 18 charts. So I'm going to go through them very quickly. And so I'm going to share my screen. Yes, so the title of my talk is Integrating Cybersecurity and Data Science, which also includes for this presentation, artificial intelligence and machine learning with applications in smart Internet of Transportation systems. Okay, so part one is going to be some of our work on integrating cybersecurity and data science. Part two of the presentation, an example secure cyber physical system, in particular, secure Internet of Transportation system. And part three is going to be applying part one to part two, which means applications of AI, ML, data science. And now the Internet of Transportation systems are going to be smart Internet of Transportation systems with all the AI techniques being applied. And so I'd like to thank my colleagues and also a variety of our sponsors and our project coordinator. And so I'd like to thank all of them. Part one, integrating cybersecurity and AI, ML, data science. Okay, so there are three aspects I'm going to discuss. One is policy aware, privacy aware, policy-based quantified self, right? So developing a data management framework. And what do we mean by that? There's so much of information that's being gathered, right? Our health information, our fitness data, location data, social media data, image, and so on. It's all being collected on our smartphone. And the whole idea is to collect all of the information so that we can give advice to the various users. So that's the quantified self movement, which is psychologists are working on it and sociologists collecting lots of data about individuals so that we can have a better society, a healthier society. But what happens? Because of all of the data being collected, our privacy is being violated because you can have individual records which are anonymized, but when you put all the multiple records together, right, it could be a highly sensitive, highly private information could be divulged. So anyway, some of the information could be in the cloud, storage, encrypted backups, some others in cloud-based services. And so some information could be anonymized. And so this is what we are developing, privacy aware quantified self-manager. So what do we mean by privacy aware? What we are saying, and we have published a couple of papers, that policies have to guide the data collection. How can we collect the data? We may have to obtain informed consent. How do we store and access the data? How do we analyze the data? How do we share the data? Everything according to policies. And these policies are not really, toy policies like I tell you a secret provided you don't tell that secret to John or Mary. No, these have to be real world policies. So we computer scientists are working on policy with policy experts to develop this privacy aware policy based quantified self data management framework. Okay, so that's one aspect. We are bringing in data analytics and data science and data sharing with security and privacy. Okay, so that's one aspect. Another aspect that we are working on, data science for cybersecurity applications, and that is big data stream classification. So what happens here? What is streaming data? Data is continuously arriving, right? So you use the past data to build a classification model. But what's happening when data is streaming, the concepts are changing. You can't have one concept. You can't say that you want to buy Apple shares forever, right? Tomorrow it could be Facebook. Day after tomorrow it could be Microsoft. The next day it could be Amazon. So it all depends. The fifth day it could be IBM. So concepts are continuously changing. So continuous flow of data is very common in a digital world. So what happens? One data science model, one machine learning model is not sufficient, right? So we develop an ensemble of models, and at every time these models vote, as concepts are changing, they are going to vote and throw away the model that is performing poorly, right? And then we test. So we have an ensemble of models. As concepts change, we throw away the models, some bad models, and then we develop some good models, okay? So if it's attacks, the test data comes in, attack, then we block and quarantine, otherwise benign traffic we serve. And with human in the loop, you know, some of the time, right? So we have to update the models. So that's the whole idea. And what did we do? We applied it to insider threat detection. What do we mean by that? We gather all of the system calls and we take I chunks, right? And then we train the models. We have number of supervised learning and unsupervised learning. And then so we have an ensemble of models, and then these models are continuously updated. And then when the test data comes in, right, the I+1 chunk, and then we again extract the features, and then we test it. And then if it's an anomaly, then we have to quarantine, right? So the whole idea inside a threat means you are bad people, bad processes, pretending to be good people and good processes inside an organization or a computer system. And we got some very interesting results. So that is data science for cybersecurity. Now, what happens if these data science techniques are attacked, right? We are saying AI, machine learning, data science, you know, it's going to be applied to lots of applications, whether it be healthcare or insurance or finance or medicine or developing these pharmaceuticals and vaccines. What happens if these data mining machine learning techniques or data science machine learning techniques are attacked? Then you cannot depend on these data science techniques. So it's not, so what do we mean by attacking? The adversary is going to modify our model or thwart our data, putting poison into our data. So we have to understand the adversary and act, right? It's not concept drift. It's not online learning. It's poisoning the data. It could be during testing time, during training time. So we both play games. So in this picture, this is the support vector machine boundary line. What's below this, the blue circles are good instances. The red squares are bad instances. So the adversary is learning about our model and see what happens. The bad instances are pretending to be good instances, and that is what we don't want. So what do? We have, okay, this is the support vector machine boundary line. All these red crosses are bad instances, and these green circles are good instances. And you can see some of the bad instances are going in here because it's figuring out what we are doing, and it's pretending to be good. What we do is move the support vector machine line to this blue line. That is the challenge. So then, once you move this blue line, look, a lot of the bad instances are now being caught, right? So now they cannot pretend to be good instances. So you could ask the question, we can move the blue line right here. That means all of the bad instances could be caught. But then what happens? The good instances are going to be shown up as bad instances. We do not want false positives. That's really bad, just like false negatives, okay? So the whole challenge for us is doing lots of mathematical calculations, and it becomes like a game playing between us and the adversary. How far do you move this support vector machine boundary line? So that is our challenge. Okay, so now we go into, very briefly, the Internet of I'm looking at the time, by the way, Internet of Transportation Systems. Okay, and what's the security? So Internet of Things, right, can be applied to transportation. Internet of Things is much broader. Your microwave connected to your smartphone, connected to your television, connected to your refrigerator and the lights and the whole lot. But here we are talking about transportation. All the cars are connected, the trains are connected to cars, and the trucks are connected to the roadworks. It's not just ground vehicles, it's also aerial vehicles like drones and airplanes, and also sea vehicles. So everything combined together, they have to all work together. But these systems could be attacked. Right? Imagine if the transportation systems are attacked, and you can have all kinds of horrible things happening. You could have accidents and so on. So we've developed an algorithm called PBAD, physics-based anomaly detection for ground and aerial vehicles. So algorithm has 3 parts. We build a model offline. It's a physics-based model. So we look at all the coordinates, XYZ coordinates, and we build the model. What's the trajectory of this aircraft or the truck or the automobile and so on. And then we implement an online tool to monitor expected and observed behavior to detect anomalies. And then so offline pre-processing, online verification, and then of course an alarm is raised if the significant residual difference exists between executions. It's a fairly sort of straightforward, you may think, but it's quite complex when you go to design it. And also we used Kalman filter in order to develop our algorithms. It's not ML or it's not AI. It has been around for a long time. The electrical engineers, control systems engineers have been using. So, but it was very effective for us. And our implementation, we did it with ground vehicles and aerial vehicles. And so these are all of the equipment we use. Aerial vehicles, essentially drones with various controllers. And the overhead was 5.4332. And then we found attacks are detected after 0.2 GPS. That is the GPS spoofing, global positioning system spoofing, 0.2 seconds, while gyroscope attacks are detected after 1.5 seconds. Similarly, ground vehicles, the overhead was less, but we focused on detecting visual attacks on the camera, attacks detected after 0.1, and the controller was ROS kinetic aim. Each threshold produces a probability of false alarms of approximately 2%, and we'd like to minimize that, right? So this was really very useful for us, and this was one of the early implementations of anomaly detection in cyber-physical systems, particularly Internet of Transportation systems. Okay, so we also focused on privacy, right? I don't have a chart on that because of lack of time, because we also want to make sure that we don't want people to see what we are doing, whether are we smoking and driving, although we shouldn't be doing that. But, things are very private, our location, various other things. So privacy is also really important of the individual. So more data being collected, the privacy could be violated. So part 3, and I think my timing is quite good, applications of AI, ML, data science for smart Internet of Transportation systems. So what we are going to do is apply part 1 to part 2, so we get part 3. So you can see my little picture I had earlier. So anyway, the whole idea, Internet of Transportation systems, how do we apply data science? So they are subject to attack. So earlier I gave an example how we detect anomalies using Kalman filter approaches. But now we are going to apply data science. So this is sort of a current work that we are examining. There's lots of streaming data that's coming between the vehicles and so on. Transportation systems go electric. We need to have energy conservation. What you can get stranded in the middle of a desert or something. So that could be very disaster if those systems are attacked. So data science ML techniques are being applied to analyze the data. And the whole question is, can some of our stream techniques that we discussed earlier, can they be applied to, say, financial data, what we have applied to financial and telecommunications and healthcare data? Can we apply them to transportation data? So essentially our physics-based anomaly detection, that's important with the Kalman filters. Can we bring in some of the data science, machine learning to give more advice and have more robust and more accurate algorithms? So that's our challenge. So the main question is to understand the nature of the complex transportation data, adapt the system analytics techniques and apply them on massive amounts of heterogeneous data. That's data science, AI for transportation system security. Then what happens if the data science and machine learning techniques are attacked? So we have adversarial machine learning for smart Internet of Transportation systems. So these systems again are going to, assuming that we are going to develop sophisticated transportation systems, smart systems. So they are going to be AI machine learning driven and perhaps without a human in the loop, because we are going to have driverless cars and so on. So adversary is not going to keep quiet. He or she is going to be watching what we are doing and our driving patterns and what we are doing, the vehicle's various aspects, and they are going to try to thwart our models. How are we applying AI? How are we applying machine learning? It's going to thwart our machine learning models, but we have to learn. We have to adapt to thwart the adversary. So just like we move the line, the blue line, Eventually, it becomes game playing between the adversary and the vehicle. So what sort of game? Is it zero sum, Bayesian, Stackelberg, right? So we need to understand the data. And research on this topic is only beginning with respect to transportation systems. So if we can do this data science and adversarial machine learning, right? And privacy-aware, policy-based data management framework for smart Internet of Transportation. If we can have a handle on all three aspects, of course, we can have smart Internet of Transportation and the corresponding infrastructures. So instead of healthcare and social media, all the data, we get radar, GPS cameras, LIDAR, ultrasonic sensors. And then here we have our car. Inside the car, we have data collection, data storage, data analytics, data sharing, because all the cars have to be sharing data with the other cars. Some of the data could be encrypted back up in the cloud for further analytics and providing cloud-based services, querying and obtaining results. So what we have is privacy-aware, policy-based autonomous vehicles. So all of the data collection, data storage, data access, data analytics, they have to be governed by these various policies, and coming up with the appropriate policies, that's the challenge. And so summary and directions, developments in AI, integrating cybersecurity AI, they are exploding, right? That's one of the hottest area now in cybersecurity. Applications of AI for security and adversarial machine learning, in particular, adversarial machine learning is being extremely important and a popular topic. And then, of course, we need the privacy-aware healthcare for managing one's life's activities, privacy-aware quantified self, at the same time with the development of Internet of Things, including transportation systems and infrastructures, security and privacy solutions are being developed. They are mainly physics-based solutions, right? Looking at the physical models of the system. As driverless cars become a reality, more and more of the AVs, autonomous vehicles, will use AI and machine learning techniques. The challenge, how can we develop AI solutions for detecting malware in AV systems? And how can adversarial machine learning work? Can we develop a privacy-aware, policy-based data management framework for Internet of Transportation? So if we do all of this, of course, then we can get a smart Internet of Transportation system. And I believe that there are numerous opportunities for substantial research. And so this finishes my presentation and my position statement. And I'll be here for the panel. So I'll be happy to answer some questions. I'd like to thank all of my colleagues. And so I'm going to now stop sharing. And so I think the key point here is that Internet of Things, Internet of Transportation, right? It's going to be the next big thing that we are going to be faced with driverless cars, autonomous vehicles. We are looking at security, but security is going to be a major, major, major problem. Imagine if these systems are attacked, it's going to be devastating. And so we need to develop solutions. And yes, we are developing physics-based solutions, but that's not enough. We need to come up with fewer false positives and negatives. It has to be accurate. And that's where AI machine learning is going to help. But then to advance Internet of Transportation systems too, we are going to use AI and ML. But the whole challenge right now is, how can these AI ML techniques, what happens if these techniques are attacked? It's going to be devastating. That's why we need to focus on data science, AI, ML for Internet of Transportation, then adversarial machine learning for Internet of Transportation. And of course, we cannot forget privacy. So privacy aware, policy-based. Policies have to govern the privacy preserving solutions. So those three are critical if we want to develop smart Internet of Transportation systems. And again, thank you very much. So I'm going to stop.